Yeah, good evening, everyone. So, my name is Mohit, and I'm working as an assistant professor, AIT, Computer Science and Engineering Department, Chandigarh University. I'm going to give my presentation on IoT evolution, unleashing cloud, fog, edge computing synergy for enhanced applications. Introduction to IoT. As we are very well aware of what is IoT, so it is basically an interconnected physical devices embedded with sensors. The sensors which sense the data, collects the data, and then further transfers the data through various communication resources to the cloud data center and maybe to the fog data center. It is typically depends on the application we are using. And as we can see in the cloud data, as we can see in the given diagram given below, that various sensors being deployed on various places at home, in mobile, maybe at energy place, maybe at a healthcare center and in a additive manufacturing center, or there are many more other devices we can induct which sends the data, then further transfers the data to the cloud data centers for the permanent storage. So this is just a use case example of IoT. Components of IoT. So these are the various different components, various important components which I am going to cover in my presentation. One is the cyber physical system, second is the cloud computing, third is the fog computing, then fourth is the edge computing, and then last one is the industrial IoT. So these are the challenges of the IoT: latency, scalability, security, sensor deployment, maintenance, utilization. So these are a few challenges which generally being considered or being observed while working with the IoT environment. For the cloud computing, so one of the component of the IoT, that is the cloud computing, and we do have some challenges. Although as we know that in the given diagram we can see in the very first slide, cloud is used for the permanent storages. So in the same manner, cloud computing do have some challenges like latency, high bandwidth consumption, less efficient in power consumption, reliability, security, scalability, maintenance, and data privacy. And the very most popular topic is today's the privacy of the data, as it should not get compromised. So continuing with the same topic, the cloud, fog, and edge computing. As we can see in the given diagram, edge computing basically is a part of fog computing, and fog computing and both edge computing becomes a part of the cloud computing. Basically, edge is nothing but a device or the sensor which sends the data. So the communication mechanism is also embedded within the edge device. So that device in itself is capable of sensing, observing, analyzing, and then further transferring the data, the useful data which is need to be sent to some other place. The fog computing have a different mechanism. Although edge computing is in its development stage, and the fog computing is highly in the advanced stage, because the concept of fog computing was introduced or proposed by Cisco in 2012, as it comes as a complement to the cloud computing. Then further, fog computing offers various aggressive features. So we're going to cover those features in the next few slides. So this is a comparison of cloud, fog, and edge computing. The first parameter is latency. So latency in cloud computing is high, in fog computing it is medium, and in edge computing it is lower. Scalability, high and easily scalable, the cloud computing. Scalable within the network, the fog computing, and in edge computing hard to scale because it has a very tiny and a few very small scale devices. Then further distance, far free from the edge, like in the cloud computing. In the fog computing, network close to the edge, and in edge computing, at the edge. That means network or the communication mechanism is also reside within the sensor. Data analysis, so less time sensitive data processing and permanent storage in cloud computing. Further, real time decides to process locally or send to the cloud. That will be decided depends upon the application we are experiencing in the fog computing. Further, in edge computing, real time and instant decision making. So it makes decisions very quickly. Then further, computing power. Cloud computing has highest computing power. Fog computing and edge computing has very limited power. Interoperability. Cloud computing have interoperability high. Fog computing has interoperability high, but edge computing I told you that edge computing is still in its development stage, in its initial stage. So edge computing has a very low interoperability. So these are the powerful features of the fog computing. Low latency, more scalable. I would like to correct. It is scalable up to some extent. Location awareness, mobility, high quality of service, geographical location, heterogeneity, and less bandwidth consumption, and obviously the low energy consumption as well. So these are the powerful features of the fog computing. So this is a use case example of the fog computing in smart health, or the devices which is being mentioned just below. At the very first layer, smart health, connected manufacturing, smart factory, smart transport. So the data is being sensed at from these particular resources. So sensed data is then further transferred to the fog cloud. Fog cloud is nothing else. This is the local servers being deployed. Then these local servers usually collects the data, analyze the data, and then further take appropriate decision depends upon the application, or it is being programmed by the programmers. Then further the data is further transferred to the cloud computing for the business analytics, or maybe for various different purposes for permanent storage. So my objective is just not to discuss that what are the difference between the cloud, fog, and edge computing. The primary objective, or the main or the chief objective, is to discuss the task scheduling and various computing paradigms. So the paradigms, basically, either it is cloud computing, or it is fog computing, or it is edge computing. So they every environment, or every computing environment requires scheduling algorithms, scheduling whatever the task they wanted to perform, the desired task. So that desired task will be performed only through some specific programmed scheduling algorithms. So scheduling algorithms being used to find the best solution that will be available. But this is a challenge in task scheduling because it deals with non-polynomial complete natured problems also. So that is being a challenge to the task scheduling algorithm. For task scheduling problems, one is the static scheduling algorithms, then dynamic scheduling, then heuristic scheduling algorithms, then further hybrid scheduling algorithms. So these are the task scheduling problems. So, or we can say these are the task scheduling approaches we basically used, different kind of approaches we used. So these are not the problems. So pardon for my mistake in the slide, that these are the algorithms. So research gaps and findings. So a few research gaps and findings we have concluded during the literature survey, or the challenges we find with respect to task scheduling in edge, fog, and cloud computing. The real-time scheduling in dynamic environment is a major challenge. The arrival of tasks can be highly dynamic in real time. However, various existing algorithms are static with respect to task arrival rates. So when the task arrives, it arrives dynamically. But the algorithms what we are using, either it is a static one or it is a dynamic one. So which algorithm we are using, is it comfortable for the present algorithm, present scenario, or the arrival of the task or not? So that is need to be observed, or that is need to be improvised or optimized. Then further, second point is to manage the heterogeneous resources with varying capacity in cloud computing, as cloud computing is a very complicated environment where various storage devices are interconnected with each other, and a few other things are also there, like analysis part, and then further storage part, then further access part. So cloud computing has to deal with various issues, so it has heterogeneous resources. So to deal with heterogeneous resources at the same time in with the task scheduling algorithm becomes a complicated task. Then further, to conserve energy consumption. So whatever the algorithm, whosoever the algorithm will be utilized, either it is a static one, or it is a dynamic one, or it is a hybrid one, that algorithm has to be has to be produce optimal results with respect to energy consumption as well, so that the maximum results can be achieved with the minimum consumption. Then further the in cloud computing environments are highly prone to power failure, network congestion, because they have to because the data need to be transferred to the far places. So it requires high bandwidth as well. So the task scheduling algorithms need to keep track on what data is being transferred, up to what extent it's being transferred, and what we have been left with. So that we need not to transfer the data from the very beginning. The moment we stop, or the moment the data transfer starts, so we need to keep track on that up to what extent or at which packet the data transfer gets stopped, so that we can resume our transfer at the same place or at the same component. Then the exploration of multi-objective task scheduling mechanisms and inspects trade-offs between multi-objects. So multi-objects, or the heterogeneous devices we deal with, holds impeccable research direction in fog computing environments. It is highly demands security and privacy requirements, such as secure task placement is a big trouble. So this is a very big trouble in the fog computing environment which is being analyzed. The task identification on edge devices is difficult due to heterogeneity of resources and varying conditions. Then the limited energy of edge devices makes, so this is with respect to the edge devices or edge scheduling, the edge computing, where the devices are very small, and the task to install or to make current present task scheduling algorithms to execute tasks on in this scenario in edge computing becomes more challengeable. The conclusion: IoT has transformed industries and data management, leading to expanded data center capacities. Challenging in latency, security, and deployment persist still. IIoT, which I forgot to introduce, that is IIoT, Industrial Internet of Things, integrated with Industry 4.0, has revolutionized manufacturing. However, deploying paradigms such as fog computing, cloud computing, and edge computing, we have to see that which paradigm is suitable, or which paradigm is more appropriate at which place while executing the application. So that things we need to be taken care of. Task scheduling challenges call for innovative solutions. Then further integration of fog edge computing is essential for timely data delivery and various application areas. Strategic choices in computing paradigms drive efficiency and operational success. So I'm going to wind up my presentation. So these are the few references which I have used during my paper making. So thank you guys. Thank you everyone for listening me. Thanks a lot.